So, as you may have noticed, actually the next presentation has already started, because the man that you saw on the screen there, and I'm not referring to the fly, but to the pianist, was actually one of our colleagues, Adrian Schubert. And this is a man of many talents, actually, because he plays the piano pretty well. Then he's a pretty good scientist. But actually, when he was a child, and he didn't tell me this, but I think I'm right anyway, he wanted to be a movie director. And actually, in the next presentation, we'll see each of these three skills combined.
So thank you very much. Welcome back from the break. I think maybe you can turn the mic down just a tad, just a little nip, a little tiny bit. So, thank you, that's perfect. So I actually had, I had trouble coming up with a title for this talk. The official title is Radar Remote Sensing. But it's a little bit of an unusual talk, so I actually came up with 3 titles in the end that are all equally valid and kind of intended for different audiences. And here they are. The first one is kind of intended for the technically inclined old schoolers. Probably doesn't mean much to anybody here yet. Maybe in 10 minutes or 15 minutes it will. This is for the aesthetically inclined. Then we have something for the young at heart. I don't see any kids in the audience here. Bats from outer space. So this is all equally valid. Now, probably you're already wondering what is actually going to be in this talk. So often, people who don't know me already, they ask me what I do. And some of us in my group have the same problem. I hesitate and I tell them, well, I'm in remote sensing. Usually this is met with a blank stare. If anything, then people will associate this usually with other concepts. This is obviously not what I mean by remote sensing. So remote sensing is actually about keeping track of what's going on this planet on a large scale. Because after all, everything is interconnected and everything is changing all the time. So to do that, we need to go up. Now we can actually do remote sensing from airplanes, but to really get a good overview, we need to go way up here. Actually, we don't need to go quite that high up. It's enough to go to about 500 kilometers altitude, where most satellites orbit the Earth, and this is one of them. It has a radar antenna on board. And a radar is a lot like a bat, because both of them use echolocation. So a bat sends ultrasound pulses out and gets the echoes back to make an image of what it sees. A radar sends out microwave pulses, just like the microwaves in your microwave oven, gets the echoes back from the ground and makes an image of that. What they also both have in common is that they can both see in the dark and through bad weather, so we can get an image anytime, any place, and that's a big advantage for radar compared to optical satellites, for example. Now, what we're going to want to do to make an image from these echoes is to figure out where each echo came from on the ground exactly and how bright it has to be in the image. So to do that, I'm going to represent each echo or a pulse as something you can see and hear at the same time, even though it's invisible in real life. So you're going to hear a group of notes, and that's going to represent one pulse coming from the satellite, and it's going to be represented by a blue disc. So here it is sending a pulse. Okay, that was one pulse. This is all happening very fast in real life. Now we're going to follow the third one we're going to follow the third one down to see where it goes. So it's following a beam, looking out sideways, and it's illuminating the ground like a flashlight. This illuminated area is called the footprint. The pulse comes down and scatters echoes from targets on the ground everywhere. So basically every point on the ground sends an echo back Some of them go back towards the radar, and they're colored blue here. And they're the ones that the radar is going to register in the end to make the image. This is the same thing from another angle. Now you see a pulse coming down and reaches the near part of the footprint first, sending up echoes as it goes back, as it progresses back with increasing distance. We're going to do this again and listen now to what the radar actually hears from one of these pulses. Okay, so, and there's going to be one more now. So this sounds a little bit like the original pulse that you heard, but it's longer, right? And that's because each echo is actually a copy of the original. It lasts a certain amount of time, but because they're not separated enough on the ground, they all merge together, they overlap. So we hear this uninterrupted echo chain. And that's bad, because if we can't tell when each echo arrived at the radar, we can't calculate the distance to the ground from which it came. So we need a trick to find out when each echo got back. We can make an image like this already, but it'll be a very bad image, not even worth looking at. So we need to be able to separate these echoes out from each other. This is our pulse. Now this is how it would look as a piano piece, and if you look at this and you're familiar with music, you'll recognize that the answer is obvious. We need a better composer. I like Frédéric Chopin. Schubert is also good. And one more time. So this is an extract from one of Chopin's pieces. It lasts exactly as long as the pulse from before, but it's increasing in pitch, which is why I selected it. And because it's a more musical pulse, I'll be representing it now with these pianos instead of these boring blue discs from before. So let's see what happens when we send down these pianos instead of these blue discs. What's the radar going to hear? Okay, they still overlap, but now we can hear them separately. If you were paying attention, if you were just listening, maybe you even counted 4. So these are just 4 example echoes that I demonstrated. So we can tell each one apart from the other. That means we can calculate the exact distance from the radar, because we know how fast they're traveling at the speed of light. So this is not bad, but there's still one problem. All of the points on one of these white lines is equally distant to the radar, which is actually intuitive, right? If you know how far away something is, it doesn't mean you know in which direction it came from. Of course, they all came from this illuminated area on the ground, but we don't know where on the white line an echo came from. So we still need another trick to be able to tell exactly where it came from on the ground. This is the same thing, but looking sort of along the beam. How are we going to tell where an echo came from on one of these white lines? Well, we have to remember that we're actually moving. And so we're moving. This is the center of the beam here, the red arrow. All of these points are moving towards the satellite, and all of these are moving away from the satellite, because we're moving forward and looking out sideways. So you're all familiar with the Doppler effect from waiting by the train station. This is what happens when something moves past you. It changes its pitch as it approaches you, and it's decreasing as it moves away. Now, of course, the Doppler effect is only a relative phenomenon. So we can move past the train, we can scan past the train, and it can be stuck on the ground. We'll still hear the Doppler shift. Right? So that means the ground does not have to be moving for there to be a Doppler effect, because we're already moving. Okay, so given the pitch of something on the ground coming back, the pitch change for that particular echo, it puts us on one of these red lines. We know which direction, whether it's more in front or behind the radar, that it came from. And in terms of our musical echoes, if we're more in front or behind the radar, of course, they're going to sound like this, in front. And behind. So you heard the pitch shift. So we actually now have solved the problem. Given the pitch of an echo, we can put it onto one of these red lines, and given the musical echo, this musical pulse, we already know which white line it was sitting on. So we've actually solved the geometry of our problem. It must have come from one of these intersection points, right? The one that applies to it. So this is the situation we have at the moment. We're scanning the surface with our musical pulses. Some of them are coming back, but there's still one last problem. If you remember, I said it at the beginning. How bright do these echoes have to be in an image? Right? An image is made up of different pixels which are more or less bright. That's the easy part. Small objects, if they're not crushed by the microwave, will send back small echoes in general towards the radar because there's not much area facing the radar. So we'll get dark pixels like this one at the bottom right. Slightly larger objects will, of course, make slightly lighter pixels in the image. Of course, larger objects will make brighter pixels still. And in Switzerland, we have a lot of these. Now, when we fly over the mountains, the sides of the mountains facing the radar act like giant mirrors, like you can see. So it sends back a lot of the energy. We end up with these really bright pixels. And the opposite can happen too. We can have a giant mirror, smooth water, it'll reflect the echo away, and we'll have a black spot in that image. So we've actually covered all of our bases. When we put that all together, we can already make a radar image. We do this by scanning as it orbits around the Earth. So this is Switzerland, seen in radar colors, so to speak. It was taken by a European satellite, Envisat, which we lost contact with, unfortunately, about a year ago. So you would think that we're done. This is what we've come down to here. We're scanning the surface in a kind of a strip. We can start or stop when we want. And you see the bright surfaces on the sides of the mountains facing the radar. So that is actually how you create a radar image from these echoes. Now, we're at a university. First of all, so just to summarize, what we've learned so far, a synthetic aperture radar is like a bat, but using microwaves instead of ultrasound. And it sends these musical pulses to image the ground, and it orbits the Earth in space. So when I wrote down these 3 points, a kind of a funny image came to mind. Based on just these 3 points alone, a synthetic aperture radar should actually look like this. I wanted to visualize that. So it's a bat sending microwaves orbiting the Earth. It's not very accurate, but kind of amusing. So we're not quite done yet. We're at a university. Sometimes they force us to do research there. And we wanted to find out how accurately can we pinpoint the location of one of these echoes on the ground. That was these intersection points that I mentioned before. Can we localize them with 1 meter accuracy, 10 meters? What is it? So to do that, we put these metallic corner reflectors out in the field, and we measure their positions very accurately with super expensive GPS equipment. And what's cool about these corner reflectors is that everything that comes in gets sent back in exactly the same direction. So they end up as very bright points in the radar images. This is us scanning the area where we have these reflectors, and it reaches a reflector and sends everything back up towards the radar. So that's what we do to get these kind of bright test points in the images. And here is one of those images. We have to zoom in a bit to see the reflectors. So this is what they look like in the radar image. And when we look at these points very carefully and measure their positions, which we can actually do really, really accurately, it turns out that we can localize their positions on the ground with an accuracy of about 8 centimeters. And that's from a distance of 700 kilometers looking along the beam, because we're in orbit and looking out sideways. That's about the size of an apple. And remember, there's nothing special about these points. They're just bright test points. So it means that every point in one of these images can be mapped to a point on the Earth in a volume of about an apple. So this analogy of the apple reminded me of William Tell, who was the famous Swiss folk hero who was said to have shot an apple off of his son's head from a large distance with a crossbow. And it's actually not the complete truth, what I've told you up until now. To get this 8 centimeter accuracy, we also need to compensate for some effects like the atmospheric pressure, temperature, and humidity changes, and even the pull of the moon's gravity, which is moving the solid Earth around and shaking our reflectors a little bit. So we need to figure all that out and subtract it from our actual radar measurement to get this accuracy, which in the end just tells us how good the radar is. So to demonstrate how cool this result is, I imagined William Tell shooting an arrow from Zurich, trying to hit an apple off of his son's head in the English Channel north of France, and he would be standing on a boat to simulate the kind of tidal effects. And he has to predict all of the weather patterns and so on for it to work. So it wasn't enough, of course, to just imagine that. I had to see it. So I made it for you. This is his son in his older years, probably getting tired of his father's archery experiments by now. Still alive. And this is his father shooting an arrow from Zurich. Makes its way slowly through Switzerland. Travels along through France. I think slowly his son is starting to get nervous, although he's had many years of experience as a human target by now. That is what you call an accurate prediction. Thanks for listening.
Thank you very much, Adrian. That was amazing. There was one thing I worried about, because we live in a pretty funky country with all these fantastic mountains. And if you throw the heritage of Frédéric Chopin at that, of course, it goes in all kinds of directions. But as you may know, I come from the Netherlands, which is as flat as a mirror. So I'm wondering, if you throw that at my country, do you just get the same back and you get a black image, or do you actually see something?
It's all black. No, of course, it's not only mountains and puppies and cows that send echoes back, but it's the radar wavelengths are about 3-5 centimeters long. So they get reflected back from anything that's about the size of a tennis ball or smaller. That means rocks on the ground, grass, vegetation, trees, and so on. So you get something back almost everywhere, except over water and over the Netherlands.
Well, that brings the next problem, because there's lots of water. And that actually brings us to the next speaker also. Thank you very much, Adrian.